Hi, in this lesson, we're going to explore how to problem solve and some different methods to problem solve in mathematics. There's a very popular four-step problem solving method that a lot of people use and not even really realize that you're using. I used a little acronym here, UDCC, to help remember. It's a good way to remember things as to the steps there. So I'm going to explain those steps or state them and explain them. The first one is to understand the problem. That means that you need to read the problem and figure out what it is asking for. What is the problem asking for? And so sometimes that might mean, you underline important information, you highlight the question, and you're understanding what it's even saying. The next step is to devise a plan. So come up with a way that you think you can successfully solve this problem. A way to solve the problem. And there's several different methods for that step that we're actually going to look at today. The next step is to carry out the plan, which means you're solving the problem. I might even name this step solve instead of carry out the plan. And then the last step is to check. In this step, you want to make sure your solution makes sense. So if you're doing a math problem and it says you kick a football and you want to see how high it went. So this is a quadratic problem, but if you come up with a solution with a negative number for the height, doesn't really make sense to the problem. So you might have to go back and check. Maybe you made a little tiny error somewhere in your solving. Or you got two solutions. One of them is negative, one of them is positive. You can say the negative one doesn't make sense, so it has to be the positive. So that's kind of what that means. We're not doing quadratics today, but that's just an example of where you could definitely use that. Some additional problem solving strategies that you can use. There's a whole bunch of strategies. The ones that I use most often are tables of values, charts, pictures, looking for patterns, writing equations, and working backwards. There's a lot more. There's lots of lists of those, but those are the ones I use the most often. I actually used working backwards in my last video with sequences. So that's an effective one there. I like algebra, so I like to write equations, but that may not be your thing. So we have an example here of using a table. This is one of my favorite examples. You'll probably see this in a lot of textbooks. It refers to the Fibonacci sequence, which we talked about in one of my previous videos. We've got this scenario. So a boy put a pair of rabbits, pair means two, in a cage. And during the first month, the rabbits produced no offspring. So 2 rabbits, no offspring. However, in each month after that, they produced 1 new pair of rabbits. If each new pair produced reproduces in the same manner, how many pairs of rabbits will there be at the end of 1 year? So what I'm doing right now is I'm understanding the problem. I'm just reading it, and I would recommend maybe reading it 2 or 3 times, especially something like this that is very wordy. So in the first go, just read the problem. Now I've seen this problem before, so that I'm kind of doing 2 steps in one, but for you, for the first time that you read a problem, just read the problem. Now go through the problem, read it again with a little bit more detail and analyzing. So a boy, irrelevant, put a pair of rabbits, one pair of rabbits. That's 2 rabbits, reproducing rabbits. And during the first month, so I've got a picture in my mind. I've got 2 rabbits in a cage, and in month 1, no babies. Okay. And then it says, but in month 2, they did have babies. So now in the cage, we have the 2 original rabbits. And then in the second month, there is, what did it say? Each month after they produced 1 new pair. So 2 more. And then that pattern continues. So you kind of have to keep in your mind that each month that there's a new pair, it's not reproducing. And the easiest way to solve this type of problem is to either draw a picture, which if you know rabbits, that's going to end up being a lot of rabbits in your pictures, or you can do a table. And in this example, in these notes, I did a table. So understand the problem. We start with 2 bunnies, and they produce another pair in month 2. So let's go down here. I've got a table started for us. Now watch the wording here. I did say 2 bunnies, but 2 bunnies is 1 pair. It says number of pairs. So in the first month, we have 1 pair, and they did not reproduce. So after that first month, we still only have 1 pair. Now in the next month, we have the 1 pair that we started with. They do reproduce a pair, which means now we have 2 pairs. So in our third month, we're starting with 2 pairs, but only one of those pairs can reproduce. And now we have 3 pairs. 3 pairs, but only the 2 in the previous month can reproduce. So those 2 pairs created 2 pairs. If you're not getting confused, then I would be surprised, but you're going to start seeing a pattern here. So if you're not seeing a pattern across this way, if you can't keep that straight in your mind, which is understandable, you might look to see if there's a pattern coming up this way. And if you're familiar with the Fibonacci sequence, which I've talked about in a previous video, then you probably start to see the pattern. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3, that next number is going to be 5, 3 plus 5, 8, 5 plus 8, 13, and so on. And that same sequence is coming up in these 2 columns. So if you can't keep track of which bunnies are reproducing and which are not, because that's so confusing, then work your way down the table instead. Whatever way you see that pattern appearing, just go with it and keep continuing it. So pause the video, fill out the rest of the table, and then come back. I do want to show you my process of filling this out, especially if you're still lost. You're going to see several patterns appear here. I already mentioned that the Fibonacci sequence is coming up, but then within the Fibonacci sequence, I'm seeing repeated patterns. So I've done the hard work. I've done the heavy lifting in this first column here. So now that I see that that pattern is re-emerging, I don't have to use so much brain power necessarily. I can just continue this down based on the previous column. And then same goes for the last column. We're still using that Fibonacci sequence. And again, we're still seeing that same pattern appear. Just make sure you're real careful in your copying, so you don't write down the wrong numbers, because that can happen. And so this last little cell in our table is going to give our final answer. And our final answer is based on the sum of those 2 numbers. So at the end of 12 months, 1 year, this person would have 233 pairs of rabbits. That's a lot. That's a lot of rabbits. You might want to control some of your breeding there if you have rabbits. So that's an example of a table, and that's an example how you can kind of see some of the patterns emerging in tables. Next one, we're going to be working backwards, which I've actually already done in a previous video with method of successive differences, but this is a more maybe relatable problem. For 3 consecutive days, consecutive just means back to back, at a crafts fair, Veronica set up a booth. On the first day, she doubled the amount of money she brought with her, but she spent $13 at a friend's booth. The second day, she brought the money with her, tripled it, and spent $35 at another booth. On the third day, she brought the same money, quadrupled it, then spent nothing. If she ended up with $235, how much did she bring with her on the first day? I will preface this problem by saying when I engineered this example, it ends up with a weird decimal that's kind of odd for money, but we're just going to go with it for the sake of the process. So it's about the process, not the answer. Basically, so we're understanding the problem. I've read the problem, and now I need to go back and understand what's happening. Basically, Veronica has come to this craft fair with a certain amount of money, and that's what we don't know. But what we do know is what she ended up with and how she got there. So if we can start with the end result and reverse that, then we can figure out how much she started with. Now, keep in mind that if we're starting with the end result and reversing it, then when it says quadruple, we're not going to be quadrupling it. We're working in reverse, which means the inverse operation. So instead of quadrupling it, we're going to be dividing by 4. And then instead of selling or spending 35, we're going to be adding 35 because we're going backwards. Kind of like that. Have y'all seen that movie Tenet? Anyway, kind of going backwards. So I want you to pause this and work your way backwards. See if you can come up with her initial amount. And I will warn you, it is a decimal and it's a weird decimal, but just go with it. All right, I've written mine out, but I'm going to walk you back through it, hopefully so that you can see what's going on. So we know that she ends with $235, and that represents a quadrupled amount because of the sentence right before it. So this was a quadrupled amount, which means that in order to figure out what it was before it was quadrupled, we have to divide by 4. And that means that she had $58.75 before it was quadrupled. Then we go one sentence above that, and that represents $35 spent. So before she spent $35, that means we have to add 35 to this previous amount. She had $93.75. And that represents a doubled amount. So before she had 93, am I on the right? Nope, I went one above. I'm sorry, tripled amount. Before she had 93.75, sorry about that. That was a tripled amount, so we have to divide by 3. She had 31.25. She had spent 13, so we have to add 13 to back it up even further, which was a doubled amount, so we divide by 2 to back up even further. And that's how we end up with her initial amount of $22 and about 13 cents. Again, kind of a weird amount, but go with it. And so now that we have this amount, you can check yourself by starting at the beginning and working your way through the problem. And as long as it ends up with this ending amount, then you know you've done it correctly. So I pulled up my calculator here so we can just double check it before moving on. I'm claiming that she came to the fair with $22 and about 13 cents, but I'm not going to round it because I want it to be exact. Again, weird number, but we're worried about the process, not the number. It says on the first day, she doubled her money times 2, but she spent 13. And remember, since we're starting at the beginning, we're not working in reverse. We're doing exactly what the problem says. Spent 13. And then she triples her money, but spends 35. And then on the fourth day, she quadruples her money and ends up with 235. So that's how I know that we've done the math correctly. Now, if you did round it to 2213, then your number is going to be a little bit off, but it'll be pretty close. In this next example, we're going to use trial and error, and that's kind of like guessing and checking. You're kind of narrowing down what you think it might be and then going from there to figure out what the solution is. So someone lived in the 19th century, that actually means 1800s, and he said, I was X years old in the year X squared. Then what year was he born? So we can kind of narrow this down. If it's in the 19th century, then it has to be in the 1800s, which means that I'm going to be around 1800 for the number squared. So whatever age he is, when you square it, it's in the 1800s range. So to figure out kind of where that is, to orient myself a little bit, I'm going to take the square root of 1800, just a kind of a guessing starting point. Whoops, pull this up. I don't know that off the top of my head. I should. 1800. That's 42.4 about. So I'm guessing he's going to be around early 40s for his age, which means I'm going to kind of go around the 40s here. 41 squared, 42 squared, 43 squared, and 44 squared. I'm going to see which one of those is going to put me in the 1800s. So I'm going to square 41. No, that's not it. 1681 is not the 19th century. Square 42. Whoops. 42. Close, but not quite. Square 43. I'm guessing this is going to be our winner. 1849. And I'm going to go one further just in case. Uh-oh, I pressed buttons. 44 squared. That's too far. So I can confidently say that the only age that when you square it is in the 1800s is 43. So when this person, I was 43 years old in the year 1849. So 43 is the original number, and then 43 squared is 1849. So we are actually looking for, if they said, how old was this person? This person was 43. This next one is actually guessing and checking. We have a fourth. This doesn't line up. This is a typo. I'm sorry. Hold on. Okay, sorry about that. That should just say a herd. A herd of cattle were seen in a field. 2 times the square root of the herd had gone to the tank to swim, and 3 times 5 cows remained near the feeding trough. How many cows are in the herd of cattle? So for this one, actually, it's not guessing it. It's kind of both. We're using guessing and checking, and we're using equations. So I wrote an equation down here. It said 2 times the square root of the herd were at the pond, and 3 times 5 were at the feeding trough, and there were a herd of that made up the herd of cattle. And so a hint here is that you're going to want to use perfect squares because of this square root. And then you're just going to kind of play around with some of those numbers and see which one checks out, basically. So we could plug in 16 and see if that came to be true. We could plug in 25 and see if that came to be true, and so on. So you're just going to kind of play with that until you find the correct number. So go ahead and check each of those, see which one comes out to be true, and whichever one is true, which means they're equal, is our solution. You can see in my calculator that I went ahead and typed in the first example. 2 times square root 16 plus 3 times 5 does not equal 16, so that's not it. 2 times square root 25 plus 3 times 5 does equal 25, so I actually don't need to go any further. This equation checks out, which means that there were 25 cows. Last example here, this is one of my favorites. I love these riddles. There's a bunch of these riddles online. Using common sense. So it says 2 US coins together have a total value of $1.10. One is not $1. What are the 2 coins? So this one's kind of tricky because you have to pay very close attention to the wording. It says 1 coin is not $1. It doesn't say that both of the coins are not dollars. It just says one of the coins. So we could have a coin, a $1 coin, and a dime. Still qualifies. One of the coins is not $1, but it still is $1.10. So that's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know. I'd be happy to help. I'll see you in the next one.